It's our last lecture together. It is lecture 43. Can you believe it? We're done after today, except for the final. There's just a little bit of business we got to do next week. Okay, a couple of housekeeping items. Everything's graded. I will say a note on homework 5.3. I had a typo on the solution, so I'm going to go through those homeworks one last time. So if your grade increases on homework 5.3, that's why. Nobody's grade is going to go down. If anything, everybody's grade is going to go up. So, but I'll probably do that sometime next week or whatnot. But I will take care of it. I'll say that as of this morning, 22 of you had done the course eval, but only 20 of you have uploaded. I have no idea who does what. So there's 2 people in here that did the survey but didn't upload proof that you did it. Please upload proof that you did it because those are free homework points you're throwing away. And for the 10 of you that haven't done the survey, please do it. Again, you can say I'm a poopy head. You can say I'm the worst professor ever. Just please do the survey because I do really appreciate the feedback, especially for a class like this where I've taught it so many times that it's really easy to sort of fall into a rut, as it were. So if there's anything that you see that should be improved next time it gets taught, I really would appreciate it. Okay, did everybody get the code? Okay. Okay, so let's talk about the exam. So you know how exam review works. I'm going to go through and talk about the format of the exam, what's going to be on it, and then the floor is yours for any Q&A that you might have in getting ready for it. So I don't have a whole lot to say in different that's different on logistics from our prior exams because I want to make the point that this exam is not formatted really any differently than any of the others. In other words, just because I have a 2-hour time slot does not mean I made the exam a 2-hour exam, because I did not. It's really just another test. I have a very strong suspicion that an hour and a half in, most people will be gone. That, again, that doesn't mean you have to be gone. You can stay the full 2 hours. But again, it's not intended to be a time-critical exam. You should have more than enough time to do the exam. It's open book, closed notes, just like with all the other exams. You can bring the manual. And bring a formula sheet, put whatever you want on the formula sheet. I'm not going to take up the formula sheets. I'll look at them, but I want you to keep them, especially given the fact that it's the final, because I've given you back the formula sheets for the last 2 exams. I'll give you back this one, obviously, as well. I'm keeping the exams, but you get the formula sheet back. Let's talk about the topics on the exam. So the topics on this exam, this is a columns exam and beams exam. So actually, the topics we've been discussing for the past couple days are not going to be on the exam. Everything on columns and beams, though, and local buckling, I should say, is fair game. Okay? So for columns, make sure that you understand the basics of how columns behave, the basics of buckling theory. So the idea about, elastic buckling, effective length factors. Why does elastic buckling not work? Or in other words, it's a useful parameter, but it's not good enough for computing column capacity because of the presence of geometric imperfections and the presence of residual stresses from the rolling process. So stuff like that, make sure you understand the ideas. As for the crux of it, what you need to be able to do is analyze columns. You need to be able to analyze them using either the AISE column curves from section E3 or table 4.1, specifically 4.1a because we're dealing with 50 KSI steel, and make sure that you can select economical shapes using table 4.1. Remember, that table 4.1 was how we would pick a shape and then we would maybe verify its capacity using the column curves. For beams, it's sort of the same idea. Make sure that you can understand basic bending theory, basic beam buckling theory. So things like what's the difference between the elastic neutral axis and the plastic neutral axis? What's the difference between, or what is ZX? What is MP? What's this whole thing of lateral torsional buckling? And why do we apply this CB term to augment the capacity of a beam? Remember, the idea is that the LTB differential equation solution assumes that moment is constant. We all know that in most practical applications, moment is not constant, so we have to adjust our solution accordingly, and we adjust that through this CB term. make sure that you can analyze and design beams. So for analysis, analysis for shear is pretty much the same. Analysis for deflection is pretty much the same. But for moments, it's a function of whether or not the beam is continuously braced or it's discretely braced. If it's continuously braced, the flexural capacity is PMP. If it's discretely braced, we got to go to our flow chart and figure out what zone we're in. If we're in zone 1, zone 2, zone 3. In design mode, if we're designing continuously braced beams, we would use table 3.2. If we're designing discretely braced beams, we would use table 3.10. Now know that if you have a beam that, independent of all the moment stuff, if it's controlled by deflection, such as a live load deflection limit, we would use table 3.3 in order to select the beam. We would abandon all the beam charts and ZX charts and just use table 3.3. That's the exam. That's what's on the exam. As for the stuff, the greatest hits over the past few lectures, well, actually, we're actually going back quite a bit. I mean, this is almost like spring break on. So it's been a while since we've talked about some of this stuff. So recall that you're going to need to know how to navigate the chart to locate K values for analysis and design. Notice that we're using the recommended values, not the theoretical one. And by the way, I'll say that this set of slides might also give you an understanding of what you ought to tab in your manual if you haven't already done so, like put a little bookmark in there. All right, so column analysis using the raw equations from section E3. This is what I've been calling method 1. So what do? We determine the largest KL over R for the column. And remember, we get the K values from the previous slide. Be careful when you're using, when you're computing KL over R, especially with your units, because remember, the length is measured in feet typically, but the R value is measured in inches, and KL over R is supposed to be unitless. So you need to multiply the length by 12 to get inches per inches and get a dimensionless quantity for slenderness. Next thing we do is we compute F sub E. That's our elastic buckling stress or our Euler buckling stress. And remember, that's the theoretical solution. And again, that's not the answer, but it's at least useful. And what we do is we take that theoretical solution, we plug it into here, because this AISC column curve, this is the AISC column curve right here, this expression for Fn, this takes into account the presence of geometric imperfections and residual stresses. Now remember, with columns, we have 2 zones of buckling. We're either in inelastic buckling right here or elastic buckling right here, and that's a function of whether or not how our slenderness falls in comparison to this anchor point 4.71 square root of E over Fy. If we're less than that, we're in inelastic buckling territory, and we use this exponential term for Fn. Remember, this Fy over Fe, it's not 0.658 times this fraction, it's 0.658 raised to this fraction. This fraction is the exponent for 0.658. If we're bigger than that and we're in elastic buckling, we just take Fe and knock it down a little bit to 0.877 Fe to account for the effect of columns not being perfectly straight or perfectly plumb. Then once we get Fn, it's 0.9 Fn Ag for the axial capacity. Okay. Method 2 is to use table 4.1. The one disadvantage with table 4.1 is that it is by default written for weak axis buckling governing the behavior. Now, if weak axis buckling does indeed govern the behavior, you can just look up the capacity. There you go. So if KLY is bigger than KLX for a W section, you know weak axis buckling governs. So just look up the capacity and move on. But if KLX is bigger, you actually don't know whether or not strong axis buckling governs or weak axis buckling governs until you look at KL over R. The thing is, you don't need KL over R for this table. You just need KL. So what you would do is, if KLX is bigger, what you do is you look at 2 quantities. You look at KLY and you look at your KL effective. And KL effective is just taking KLX and dividing it by this RX over RY ratio, and just look up the capacity based on whichever one of those 2 is larger. Now, there is a good chance that you're going to have to linearly interpolate the table, so make sure you're comfortable with linear interpolation. And as for designing a column, we get our factored load, we determine the largest KLX and KLY for a column in question, and then we use KLY to select a group of trial shapes. Remember, we select And we try and select at least one W8, W10, W12, W14. Know that it is possible that some of those sections might not be available, so if you have a pretty heavy load, you might find that there is no W8 that works. That's not an unreasonable thing that could happen. For each one of those columns, you do need to assess whether or not they're actually valid solutions. Now this isn't all that necessary if KLY is bigger, just pick the lightest one, but if KLX is bigger, what you got to do is you got to check each one of them. You got to check each one of them by checking against KL effective. If I was on an exam, what I would do is I would take all my trial sections and organize them by weight and start vetting the lightest section first and then go from there. And as soon as I find a section that works, I know I picked the lightest answer and I stop. So, but I do think it's a good idea to analyze that section using method 1 because you've done a lot of linear interpolation, a lot of guesswork maybe as it were. So actually going through and analyzing the section using method 1 is pretty important to make sure that all your math is correct. That's all we got for columns. Let's talk about beams. So for beams, the first thing that we did is we discussed MP and this term ZX. The MP is the plastic moment. Remember, the idea is that as you take a section and you start increasing the amount of bending, the bending stress profile goes like this, and it keeps increasing until, bam, you hit Fy. That's the yield moment. But if you keep increasing moment, what happens is that yielding will start to penetrate throughout the section. And when you get to the point where every cross-sectional fiber has reached Fy, now you're in MP land. Okay? Now the way that you compute MP is you take Fy and you multiply it by Zx. And what is Zx? Zx is just the sum of the products of the areas of the cross-section times the centroidal distances. So remember what you do for Zx is the first thing you got to do is you got to figure out where the plastic neutral axis is. That's the point where the area above equals the area below. Oh, I didn't mean to click that. Sorry. You click the. You find the point where the. Go back. You find the point where the area above equals the area below. We call that the plastic neutral axis. Then you start summing moments of area. Area times moment arm. Area times moment arm. Area times moment arm. Until you sum those products up, and that's your ZX. Okay. Next, I've got all of the design aids that are relevant for beams. I would say probably the one we spent the most time with was table 3.2. That's probably the aid we spent probably the most time with this whole semester was table 3.2. We really referred to table 3.2 for weeks. Table 3.2 has a lot of information baked into it. It's got the ZX, the VMP, VMR, VBF, LP, LR, all that stuff. So whenever we're designing, what we would do is we would find our required VMP or our required ZX, but we would go up to the next bold row, and that's the one we would pick. That's because within each of those groups, the bold row is the one that's the lightest. So for example, if you look at this upper group right here that's headed by the W21 by 55, all the sections below that are heavier than the W21 by 55. So if you needed a VMP, let's say a 450, you'd go, okay, 450, that'd probably be this section, but I might as well use that since it's lighter, okay? So that's kind of the idea there. If you have a section that's governed by deflection, in other words, you go through and you check the moment capacity, or you select a section based on moment capacity, it's no good. Abandon all the table 3.2 and 3.10 stuff and select a section based off table 3.3, which just organizes the shapes based on their moment of inertia, and you've got the similar grouping where the header row is the one that's bolded. Table 3.10, that's our LTB chart. So that's the one where we go onto the x-axis with LB, and we go onto the y-axis with not MU, but MU divided by CB, okay? Because MU over CB is used because this chart is crafted based off a CB value of 1, okay? And that goes into the process that we use for design, which I'll talk about here in a second. We designed 2 classes of beams in this class. We looked at continuously braced beam and we looked at discretely braced beams. Let's do the continuous case first. So remember, if you're dealing with a continuously braced beam, that means you have an LB value of 0. Yeah, because that means the unbraced length is 0. Okay. So what do? We compute our factored moment. If we're not given a beam self-weight, we should assume one. Common assumptions are anywhere from 50 to 100 pounds per foot. I will tell you on the exam, if you need to assume a beam self-weight, I'll tell you what it is, okay? Because I can have 30 assumptions and all of them are right, and so I don't have to do that. The next thing that we'll do is we will compute the required moment of inertia based off our deflection limits. I should say that if we're given, or if we're not given deflection limits, we could just skip step 2. It's possible that you're told, just design a beam with no deflection limits. So just don't worry about the required moment of inertia. Just select based off MU, okay? But assuming you've got deflection limits, you'll, after step 2, end up with a required factored moment that you need to withstand and a required moment of inertia that the beam needs to possess. So if it's a continuously braced beam, we'll go into table 3.2, pick the most economical section that we can find that has the required flexural capacity, and then make sure that that section has the requisite moment of inertia. If it doesn't have the requisite moment of inertia, skip table 3.2 and go to table 3.3 in order to select your section. Okay. Once you have a section, check your 3 limit states: moment, shear, and deflection. Moments are probably the one that are the most critical to assess, especially if the beam is heavier than what you assume. Okay. Now for discretely braced beams, there's a couple other parameters we got to consider. Number 1 is our CB term. Remember, CB is the moment adjusting factor that accounts for the fact that when we derived our LTB solution, we assume that moment is constant, but it's not in most practical applications. It's variable. So CB is a factor that accounts for moment gradient. Okay. When you're computing CB, what you do is you have a CB for every unbraced segment. Okay. So if you had a beam with, I don't know, 11 braces, and you'd have 10 segments, each with their own unique CB term or potentially unique CB term. Within a given segment, what you got to find are 4 quantities. You got to find the moment at quarter points. So if the unbraced segment is 20 foot long, find a moment every 5 foot. And then you also got to find the maximum moment overall within that entire segment. Okay. In this example here on the slide, the quarter point moment in the middle and the maximum moment just happen to be the same thing. Doesn't always have to be the case. Whenever you're calculating CB, you always take the moments as absolute values. So if you have positive and negative moments, just take them all as positive and compute the CB accordingly using the expression above. The LTB capacity chart can be just sort of organized like this. This is the flow chart perspective. I find that the flow chart is a little bit easier to navigate on a formula sheet type perspective than maybe the curve. So what we're doing is we're looking at LP and LR first to figure out what zone we're in. We're in zone 1. That's a beam that's got oodles and oodles of lateral bracing, or enough lateral bracing that buckling isn't going to occur, and we don't need to consider LTB. And then our flexural capacity is just VMP. If we're in zone 2, which zone 2 is the most common zone for most of the design problems we'll be dealing with, then our capacity is based on that linear expression as shown. That's just linear interpolation between VMP and VMR. And if we're in zone 3, we got to chug out our elastic buckling solution. For zone 2 and zone 3, there is a cutoff that no matter what you calculate, you're limited to VMP. Because I don't care what you calculate, the maximum flexural capacity possible that we take according to the spec is VMP. So that gets us into discretely braced beam design. So the process is very much the same for continuously braced beams as for discretely braced beams. You just have to, for one, you have to calculate your CB term for discretely braced beams. So after step 2, we're not just going to have a moment, and we're not just going to have a required moment of inertia. We're also going to have this. The other thing that changes is that we go into the manual and go to a different chart. Instead of going to table 3.2, we go to the beam charts. And so that's where we have to divide out the effects of CB, because table 310 is based on a CB value of 1, and then analyze the section. In discretely braced beams, analyzing that section is incredibly necessary because of the idea of false positives. What happens with a false positive? That's what happens when you have a really high CB value and you look up a section in 310, but it actually doesn't work because if you check the phi and p, what happens is the CB term tended to artificially augment the capacity, and when the capacity is really limited to this, that section's no good. So you have to keep iterating and going to section or table 310 in order to find the section that works and go from there. That was a lot. I rattled off quite a bit. Okay. We got about 30 minutes. The floor is yours. So any questions that you have about the pending final, which will be on Friday in the morning. Everybody just cooked after this semester, just done. Here, Dr. Mike, this is a Thursday night problem. What are you talking about? You're too early, man. Again, we drew the short straw on the the timing. So our finals last. I can't do anything about that. Any questions at all? Well, I got my words per minute down, I guess, after that.
There will not be additional topics. They will not be included.
No, I'm not going to put those on there. That was just cherries on top, just to cover it. Just because, yes.
I have one short question. When we calculate moment of inertia based on deflection limits, the answer we get is a minimum moment of inertia, right? Everything has to be higher than that?
Yes, yes. So the question was, just to make sure we're all clear, so when you're in, let's say, step, and it doesn't matter if it's continuously braced beams or discretely braced beams, but when you calculate the required moment of inertia based on your deflection limits and you get this IX required, that IX required is the floor value. So in other words, if you get a value of 856.3, you need to select a beam that has a moment of inertia bigger than that. Could be equal to that, but you're not going to find a moment of inertia equal to 865.3 in the manual because they're always whole numbers. So you're going to end up picking a beam that has a moment of inertia bigger than that. Because remember, moment of inertia is a measure of the beam's flexural stiffness. If that value is really small, that means your beam is really flimsy. Okay? So what that calculation is saying is this is what it needs to be to meet this deflection limit. So if you're going to pick something, you're going to pick something that's at least that, if not stiffer. Am I getting off easy? I am. Any questions? Let me just probe you a little bit. Any questions about columns? Anything about columns? I know it's been a while since we talked about columns. Anything about columns that, or are you, everybody good? Questions about continuously braced beams, discretely braced beams? Any questions about life? All right. Going once? Going twice? Well, I'll say this, for a few of you in the room, this is probably the last time, or actually for most people in the class, it's probably the last time we'll have class together. So it's been a blast having everybody in class here at Marshall. I know that some of you, this is it. You're going off to the free world here very soon. So my congratulations to you all. For those of you that are going to be around next year, I'll be around if you need me. But with that, it's been an absolute blast, everybody, and I will see you all in a week. That's all we got.